Hey everyone, back in a new awesome video, and today we'll continue with our series about classical mechanics. Today we will understand how to solve in general any pulley system. First, we will set up the system and write all of our equations of motion. Then we will understand how to use the constraints of the system to find new equations. And finally, we will understand how we can join different parts of the system together so that it is easier to solve. So let's start! Alright, so let's start setting up our system. In this video, we will treat a system consisting of a pulley right around here, we'll call A, and a pulley over here we'll call B. We are going to have a string that goes over here, and then it goes over here, and finally it goes down. We'll have two masses. This is going to be mass 1 or object 1, and then we will have an extra rope rather than a string. These are ropes, and we'll have mass 2 right around here. Now let's make some simplifying assumptions. First of all, we will assume that, let's say that the mass of the pulleys is more or less 0, so that they don't play too much of a role in our system. This could be done, but this could be done by making masses 1 and 2 much bigger than masses of A and B, so that they are not relevant in the mass scale of our system. Furthermore, we will make the mass of our ropes more or less equal to 0. That way we will have an ideal rope, which will mean that the tension T is equal along the rope. This will be very useful in our analysis. Later on, we will treat massive ropes, but that will be trickier. Now, let's see what systems we are going to have, in which different parts we are going to divide this system. We will have, first of all, pulley A. That's not an L, it's straight E, pulley A. Then we'll have pulley B. We'll have also mass 1, and finally we'll have mass 2. Now the next step is to draw 3 body diagrams for each of these objects. We will start with pulley A. We will draw pulley A right on here, and pulley A is being applied a force of tension in this direction. We'll call it T1, and it's applied a tension from the principal rope in this direction and a tension from the principal rope in this direction. It is very important to indicate in every one of your free body diagrams what the unit vectors are, and we will indicate, in this case, this is J hat A. It is not necessary that all of your unit vectors are equal. The only thing that is necessary is the signs are consistent between your choice of unit vectors for each free body diagram, and everything will work out. Then we have pulley B system, which is going to be pretty similar, and it's going to be Well, I'll draw it in black to keep a consistency, and it's going to have a tension. We're going to call it T2 in this direction, and once again it's going to have T and vector j hat b. Now let's explore the free body diagrams of the different masses. Let's draw mass 1 over here and mass 2 over here. Mass 1 has a tension, and it's tension T because it's the one of the principal rope, and it's going to have a weight m1g. Note that in the cases of the pulleys, we are not noting the weight because we said the masses of them are really small, and therefore this component is going to be really small compared to the tensions. In a similar manner, we will have this will be j hat 1, and we'll have T, and this will be not T but T2 because it's this rope, and it's the same as in case B, and we will have again the weight m2g and the unit vector pointing up. So let's denote each of these diagrams so not to be confused. This is A, this is B, this is 1, and this is 2. Now let's write the equations of motion, the F equals ma analysis for each of these systems. Note that there is only one direction relevant to the problem in each of the different free body diagrams, and therefore we will only have one equation per body. We will start with the pulleys, which we have that T1 pointing up minus 2T equals 0 because the mass of the pulley is really small. So in the remote case it moved, but it doesn't seem it's going to do so. It doesn't matter. It will be 0, or it will be approximately 0, and 0 for all instance for our approximation. Then we'll explore the case of B. We have T2 pointing down and 2T pointing up. So it's going to be 2T minus T2 equals 0. Then we have mass 1, which we have T pointing up and m1g pointing down. So this is T minus m1g equals, and in this case we have acceleration m1 a1, and finally the last body, which has T2 pointing up minus m2g pointing down, and this is equal to the mass times the acceleration. We can easily see that T2 equals 2T and that T1 equals 2T. If we substitute that in here, we find out we have T equals m1a1 plus m1g, and that 2T equals m2g plus m2a2. However, note that we have two equations. That seems okay, but we have three unknowns because we don't know T, we don't know A1, and we don't know A2. So we have some trouble over here, because even if we combine these two equations, we will have one single equation with two unknowns, and that means that we will have an infinite set of solutions. So there's something missing. Alright, so let's try to find which is the equation that we are missing. Our intuition tells us that there has to be something that relates the accelerations of these two bodies, because it is impossible that this one goes up crazily and this one goes up too. it wouldn't make physical sense for this system to go all up under the influence of gravity. So there has to be something going on. And let's denote gravity, because I forgot to do so earlier, but it was understood, I hope. Now we need to think about things that are constant in this problem. And one of the things that will be most useful in these pulley problems is to think on the length of the string. This is going to be defined as L, length of the rope. Sorry for calling it string one and over and over and over and over again. Alright, to find which is the length of the rope in terms of the positions of our objects, we need to be quite more rigorous about all this system. And let's denote some position vectors. Let us assume that this is y equals 0, and we will denote the position of our object 1 as y1 of t. Similarly, we will denote the position of our object 2 as y2 of t. Then we see that the string goes from 1 to the pulley A. So our relevant piece of information will be this distance that we'll call S, because it's constant. So it will be S1, or better SA. Then it will be relevant this angle that the string is making. So if we denote this radius by r, we will see that this length of rope is pi times RA, and similarly this length will be RB, this radius, so that this length is pi r. Once again, we will need to have this defined, but note that the position of B does change in time. Therefore, we'll have to have a variable yb of t denoting it. And finally, we just have this SB that, is just SB that joins, it's a distance between these two variables. Therefore, let's see how we can express the length of the rope in terms of all these quantities. This first segment of rope will be y1 of t minus SA. Then we will add pi RA, as we talked before, plus pi RA. Then we will need to add this small segment of rope, which will be yb of t minus SA. yb of t minus SA. Plus this pi RB, I'll write it over here, pi RB, and finally we'll have this segment of rope plus yb of t, and we know this is equal to L. The next step will be to differentiate all of this, and as we know, this is a constant because the length of the rope should not change. This is going to give us a new equation. However, we first want to express yb of t in terms of y2 of t, and the only difference is that we have an SB over here, but let's do it anyways. So we have that yb of t equals y2 of t minus that SB, And then we need to plug this into our equation right here. So we'll have that this is equal to y1 of t minus sa plus pi ra plus, and then we will plug this in, y2 of t minus sb minus sa plus, and all of this pi rb plus, and we'll substitute once again y2 of t minus sb equals L. Now we are ready to differentiate this. If we differentiate once, we'll find out that y1 of t, with respect to time obviously, y1 of t is going to be b1 of t. This is a constant, so it will go out. This is a constant too. This is not a constant, so we'll have b2 of t. This is a constant once again, another constant, another constant. This is not a constant, b2 of t, and this is a constant and this is a constant. So this will equal 0. If we apply differentiation once more, because our goal is to relate the accelerations, we'll find out that this is a1 of t plus 2, and we'll differentiate a2 of t equals 0. And this is the third equation that we need to solve our Pulley system. This can be easily known from now on, and it will be left as an exercise to the viewer. Alright, we have learned to solve any Pulley system we want, because this approach will work in general. However, we need to find some new trick that will help us analyze more difficult situations. Remember, in the first segment in the video, we divided our system in 4 parts. The first one was Pulley A, the second one was Pulley B, the third one was mass 1, and the fourth one was mass 2. But there's something that we can see in this system, and also we have seen in the equations, and that is that B and 2 are very closely related, because this rope that is joining them makes sure that they are at exactly the same position along time. Therefore, we can effectively treat all of these B and 2 as a compound part of our system, as for example we'll call it 2B, and we will simplify a lot our system in lots of situations, because if we join these 2 together, well, probably that's not the best notation because it appears to be including mass 1, so let's do it with an arrow. We'll have part B will start to be called mass 2B, and in this case we will only have to do 3 equations of motion, 3F equals ma analysis, 3 body diagrams, and this will simplify greatly our system. If we have, for example, 8 bodies, 8 pulleys and masses and everything, and we can combine 2 or 3 of them, we are making huge simplifications to our system. For instance, let's analyze the situation in this case. Now we are going to have our compound body 2B with its j hat vector 2B, and we will draw inside of it the different parts that make it up, just for illustration purposes. And we will see that this body is going to feel a mass, a weight, that is going to be roughly m2bg, which is equal to m2 plus mb times g, which is roughly m2g, as we are assuming that mb is more or less 0, and it will also experience the tension from the rope, so we'll have t, and t. If we do F equals ma analysis, we found out that this is 2t minus m2g equals to a2, as it's a compound object, so it will be a2b or a2. It's indistinguishable because there's only a displacement between them, but it keeps constant, times the mass of the compound system, which we said was m2. This saves us a lot of work, and furthermore, it already combines for us some of our equations of motion. So it is very useful to, before you start trying to solve the system, see in which parts you are going to divide it. And can you combine some of those parts? Can you combine 3 of them? That will be great. And after you have done that, then you start doing your analysis and you start to find your constraint equations. That is all for today. I hope you understood how to solve in general any Pulley system, and you now can confront all of those problems you had trouble with. Remember that any doubts left, you may ask them in the comment section, and I'll try to answer them in the best way I can. Remember to like the video if it was the case, and also to press the subscribe button and the bell so that you don't miss any of the new videos. I hope you liked it, and see you another day with more Physicawesome!